yes, thank you. So hold on. So that was the example that I showed you last time. Remember, and the idea was that we said, well, we want to predict a binary task where we have the probability, like here, probability of, let's say here, death is given by a linear combination of the different input variables, right? The oxygen saturation, for example, temperature, coughing frequency, and so on and so forth. So we assume that we have W1 times X1 plus W P times XP. We have these P input variables plus some offset, I don't know, call it B, and so on. And so this probability of death is somehow related to the linear combination of that. And of course, the linear combination of these input parameters is not a probability function. So what you do is you squeeze that into a function that maps any real number into the interval between 0 and 1. And this sigma is called sigma of t is defined by 1 over 1 e to the minus t. This is the logistic function. Okay, and the task is, well, I mean, can we learn by examples these weights that give us the linear weights between the input parameter, and if we can do that, can we somehow predict the probability here of death or not? Okay, so that was the assumption. We have our output variable. In that case is Bernoulli distributed. That means we have the event death is 1 and then not death being 0, and we have our output variable. I call it Z is Bernoulli distributed with 0 and 1, right? And what you have here is this very easy distribution. You have the 0 here, and you have the 1 here, and you have here the probability for 1, for 0, and you have the probability for 1, and this here is sigma W transpose times X, and this here, oops, and this here is 1 minus sigma W transpose times X, right? So this is how you can approach that. Yes, so very general. So in the general setting, you have your, so I've just generalized that going away from that example, but it looks pretty much the same. You have an input random variable X, your output random variable Z is assumed to be binomially distributed. That's exactly what I was just drawing here. And what do we say that Z is Bernoulli distributed with the parameter P. And you said that P is sigma of W transpose times X. Okay, and perhaps I'm already, I mean, I should put some clarification probably now on this offset. But I mean, I have the I have this linear combination W1 X1 WP XP plus this offset B, if you go to homogeneous coordinates, you can, instead of taking input X, you have your X with the last variable 1 in RP plus 1. This is also sometimes called homogeneous coordinates. And if you use this notation of your homogeneous coordinates, you can shortly write this W transpose times X, right? And the B, the former B, is the last entry of your weight vector here. Okay, so this is just another shorthand notation that simplifies our life. And this is why I write here the W transpose times X. Okay. Good, so that's the assumption. The parameters of the distribution of Z depends on the linear combination of the inputs. Sigma here is 1 over plus E to the minus T, the logistic function. Okay, so far, so good. Now, what we want to do now is, well, I mean, we want to find an approach or an optimization problem that allows us to determine the best weights, right? The best weights that, that allows us to determine the best weights. And we have, like always, to define what do we mean by best. And it's a very common approach in machine learning to look at the following. So we have an assumption on our model. We have a model assumption, and the model depends on some parameters, the W transpose here. And on the other side, we have some observations. And what we do very often is we try to find the parameters that best explain the observations in terms of that maximize the probability that the observations that you observe, the probability observations, which is called the maximum likelihood approach. So assume that we have these observations. So we have training data of, we have n different training data with input variable x1 and output z1 up to xn to zn. This here. And xi, as we said, are our input variables, and zi are between 0 and 1. Okay. And so these are our observations. And we assume that the observations are independent. Independent from each other. And so we can use our model and say, well, the probability for our observations, let's call this set D, because I don't want to write all the thing again. I'm too lazy for that. So the probability of D, given our model W, is nothing else than, so you have your product, pi from E is 1 to n. And well, you have the number of death. This is this probability of death, sigma W transpose xi to the power of zi, right? Zi is either 1 or 0. And you have 1 minus sigma W transpose xi to the 1 minus zi here. right? So this is what you observe. So and you have n times, or you have a few times death, and this is the probability here, and then you have a few times non-death, and this is the probability there. What you want to do is you want to find the W, excuse me, the W that maximizes this probability. And for optimization purposes, you often don't go to the to this direct product of the probability, but you go to the negative logarithm of this maximum likelihood probability. So what you want to optimize is this term minus logarithm probability dw, which is minus the sum e is 1 to n zi times logarithm of sigma w transpose xi, right, plus plus 1 minus zi times logarithm of 1 minus sigma w transpose xi. So this is the optimization problem that you want to solve.
So one question: why are you using minus log probability? Is this the only way, or there some other ways?
Well, if there are also other ways. I mean, if the probability is something between 0 and 1, so the logarithm is negative, and people want to deal with positive numbers, so they take minus the logarithm.
But just about the choice of this kind of loss function. So are there other choices possible for logistic regression, or this is the way we go?
This is the way we go. I mean, you can normalize it. You can normalize it with a normalization factor that normalizes over the numbers of summands that you have in your sum. You can have this 1 over n, and which we have in our other approach. If you remember,
Yes.
But actually,
and also maybe if you want to weight subsamples, we can also add something like that in the summation, right? If we have some, for instance, if the distribution of the classes is not uniform, or will it not make any sense if we do it like that?
I don't see the motivation here. If you say that, do you know something about that?
No, I'm just asking in the sense that, for example, if we are saying that we have class 0 and with class 1, but if the underlying data distribution is biased towards, let's say, class 1, then is there any way that we could weight these samples?
Well, you can always weight the samples, and okay. So the problem of having a very biased training data set towards, because the observation of death is perhaps very seldom, and then you want
especially in this case, because this is a very anomalous. I mean, the probability of death is very low in that sense.
Yeah. Well, I mean, you can weight that, but then it's not. But then it's not this approach anymore, and then it does not. It's not the maximum likelihood. But then you go to another. Then you optimize another distribution that you weight towards the more seldom approaches.
Okay.
I mean, it's the same than just neglecting observations that you have, although you have them, and then this biases your distribution.
We deviate from maximum likelihood principle then.
Yes, deviates from the maximum likelihood. That's what I would say here. Was that a question?
No, it was just a comment or just an inquiry.
It's a general it's a problem in general if you have biased training data, and often you weight that, or you cut your training data set and so on and so forth, but that's more engineering than statistics. Are there any questions so far?
No.
No. Okay, so yes, so we have let's summarize. We have this model of the Bernoulli distribution of our output variable Z, and we say that this parameter, which is only one parameter in the distribution, depends on the linear combination of the input variables. And with this approach, we want to with this approach with this model, our approach is to estimate the maximum likelihood. That explains best our observations, and this leads us to this optimization problem here. Okay, now this is what we had. This is what we had on the one side, but on the other side we also had, if you remember last time, the observation, the optimization problem from this optimization approach. And what I would like to do with you is to show that actually both are equivalent and that they lead to the same weights here. Right? So we have to show that the optimal weights for the probabilistic approach coincide with the weights from our first approach that we discussed last time, and this approach was this optimization problem here, right? Where we had this loss function and replaced the 0,1 loss with this function here. And I would like to show that to you and derive it together with you and see that this is the same. But yes, so let's see what the technique is doing here. Stop that. Stopping here. And let's go to the whiteboard, because I think it's better to write things down. So you should be able to see the whiteboard now. Yes, Umer? Okay. So what I would like to show is the equivalence. So we have here minus the logarithm of the probability of these observations, d given w, right? This term. And as we just saw, this was just minus the sum of e is 1 to n for our training data. I mean, you don't have to write that down. I mean, you just try to follow what I'm writing here. It's also written in the lecture notes, so there's no need to copy that. Just try to pay attention and ask critical questions. Yeah, so that was this set I, and we had the logarithm here of this probability that came with this logistic function sigma w transpose xi plus 1 minus zi, and then the logarithm 1 minus sigma w transpose xi. That was it, right? In these brackets. And yeah, and it actually it's the nice property of this logistic function. So first we have to see that, and this is the definition, 1 over 1 plus e to the minus t. Logistic function. So the properties here are the logarithm of sigma of t is, well, this is clear, you have just minus the logarithm of 1 plus e to the minus t. And you also have this property that the logarithm of 1 minus sigma of t, right, which is actually the probability of 0, right, of not death, here in the middle. And this logarithm is, so I mean, you just plug that in and you see that this is the logarithm of e to the minus t divided by 1 plus e to the minus t, which is, it's an easy calculation, but you should have done it once. E t plus 1. So this is nothing else than minus logarithm of 1 plus et, right? So with that, if you have that, then that means that this this term here, that this term simplifies to, okay, so this is the minus sign, and the minus sign cancels the minus sign here of the sum. So this is sum I is 1 to n, and then we have Zi logarithm of 1 plus e to the minus w transpose x, right, plus 1 minus Zi, and here we have a logarithm of 1 plus e to the w transpose xi. Okay. Now, I mean, now the Zi is either 0 or 1, so we can simplify these n terms and saying that, okay, so I just sum up over, so I take the sum here for all, over all, okay, so this does not write here anymore. I take the sum here of all Zi equal to 1. And then I have the Zi sorry. Zi is 1, so I don't have to rewrite it again. So this is just in the sum Zi is 1, logarithm of 1 plus e to the minus w transpose xi, plus, and here we sum up all the Zi 0, and then this leading term here is 1, and we have here the logarithm for 1 plus e to the W transpose Xi. Okay, so far so good. Keep in mind that we would like to approach our first this other term for our optimization problem. So what we need to do is we have to replace the Zi by the Yi, and we had the classification was that if Z is 0, if and only if the Y is -1, and we have Z is 1, if and only if our Y was 1, right? So what we have to do is I have to write down this cost function again. So that means that this minus log probability T W is, so we sum up for the yi equals 1, and then we have the logarithm of 1 plus e to the minus yi W transpose Xi. I mean, this yi here is, we can insert it without any harm because yi is 1 in this sum. Okay, plus, and then we have the sum here, yi is -1, and we have this logarithm of 1 plus e, and now we plug in here minus yi, which is the same than 1, W transpose Xi, and so we have the same terms everywhere, and say that this is the same than the sum over all I is 1 to n of the logarithm of 1 plus e to the minus yi W transpose Xi. Okay, and we see that this coincides up to a scalar factor the scalar factor 1 over n with the previous approach. Okay, so yeah, so actually it's a rather easy computation, but we have to be sure, of course, that both approaches lead to the same optimal weights, and that's what they do. Perfect. That so the switching between the whiteboard and the slides takes some time, but I'll do it. So there are a few questions here. Shall we just gather the questions?
Yeah. So a student is asking, where did yi come from?
Well, I mean, we had two approaches, right? I mean, in the first approach, we had the y coming from the L01 loss, and we modeled our output variable with 1 and -1. And in the other approach, coming from the statistical approach, we model our output variable with 0, with z being either 0 or 1, and we have to map that down. So somehow going back from this categorical variable, what does it mean, death or no death, right? In our first approach, it was modeled with -1 and 1, and the other was 1 and 0. And so we have to substitute it again. in order to compare it.
And yeah, there are two other questions which are basically related to the fact that we are showing the equivalence of this statistical and non-statistical approach. So one is, when would we use one approach over the other?
Well, I mean, you end up with the same cost function. So it's a question of what do you mean by usage, right? I mean, the cost function is the same, and you can have two different. So okay, so you can have two different looks at logistic regression.
Yeah.
You can approach it from a statistical point of view, and you can approach it from an optimization point of view.
Yeah.
And you know, I mean, the idea is, or also the idea in this lecture is that I try to open you different perspectives on different algorithms, because it allows you to generalize and to understand better what people are doing in that field.
Yeah.
So it leads us to the same algorithm, but you know, if you for example want to modify now something, right? I mean, you can, if you come from the optimizational approach, you can say, well, I can just choose another convex replacement, and it also gives me a good algorithm, perhaps, right? And here you can say, well, I choose a different statistical model, and it can lead me to a different algorithm. So you're at the same point, but this perspective drives you in one direction, the other perspective drives you in the other direction, and depending on the concrete problem that you have, one might be better than the other.
Yeah.
But here at that point, it's completely equivalent. This is what I showed here.
Yeah, and the other question also relates to that. So is it possible to solve the minimization problem for the two approaches and show that the results are the same? So,
well, this is what I just did.
Yeah. So the loss functions are the same, so arguments are also the same. So yeah.
Yes, the loss functions are the same up to a scalar factor.
Yeah.
And so the minimum is, or the optimal point is the same.
Yeah, that's all.
Okay, that's all. So I think we have we have a little break, like 3, or let's say 4 minutes. 4 minutes break, and then we continue. Good. Yes. So I have the feeling that it's somehow really easier if you're in the classroom. I don't see the faces of the students, which makes me kind of feeling unsafe. I don't know how much you understood or not. So I mean, please, if there is something you're hesitating about, just try to write the comments here in the chat. Okay, so that's the only way I can get some feedback here. Okay, good. So okay, so there were some questions to the lecture to the tutorials. I will ignore them. So logistic regression. So let's summarize it. Summarize it so far. We had our input random variable x. This random variable x was in RP, and we can sometimes also go here to homogeneous. Homogeneous coordinates. x1, right? And then that makes it easier because then we can go to our cost function f of x is w transpose times x. Notation is easier. This is the only reason for doing that. We have a loss function that measures the deviation of our output and our input. That was this candidate here. We even have a probabilistic interpretation. So that's also a nice thing about the logistic regression. So once you have a new input x coming and you have your parameters computed, you assign the new class to this input by looking at the sign, but you can also compute the probability here that given your input parameters that your prediction is correct. Okay, so that also comes for free with this model by just plugging that in. Yeah, so it's not only binary classification test, but you can also say how safe you are in deciding whether a patient now is dying or not. That was the summary. I want to close this section with a few questions. So, are you ready? And then you can vote yes or no. Once you're here, okay, ready? That's good. So, first question is, do you like logistic regression? Yes or no? That's an easy question. Just to see whether you're here. Okay. Oh, that's good. Okay, someone doesn't like it. I see. Okay. The vote is for. Yeah, that's if you like it. If you don't like it, are there some reason why you don't like it for those that don't? Okay, won't change his mind. I mean, if you want to discuss about it, I don't know. We could start and then write something in the chat saying it's not good because I don't know. The method is too easy. We only have a linear combination of the input variables and so on and so forth. But yes, so I also like it because it's an easy method. It's quick, quickly implemented, and it very often gives good results. So I actually like it. And if you have a classification problem and you don't know anything better, you should probably start with a logistic regression approach. That's my advice. Okay, so that was the first question. Second one. Okay, that is also an easy one. Logistic regression is a supervised classification method, yes or no? Yeah.
So students, kindly please vote once again because we had to erase the previous votes.
So yes, question 1. Logistic regression is a supervised classification method, yes or no? Oh, okay, so clear. majority vote for yes. I mean, you know, we only count valid votes here in this lecture. So one is against it. So it's not a supervised classification method. So it is a supervised classification method, the way we defined it, and because we have an input and we have an output variable, and we have observations that that allows us to estimate the distribution also of the output variable, and so we train our method towards an output variable. So this is a supervised classification method. Is that clear for the one that voted for no, or is there some discussion? Okay, good. Some discussion needed. Perfect. Next question. The optimization problem for logistic regression is convex. Yes or no? So we have. Okay, we have 4 that say no. 5 that say no. Okay, might stick to your opinion, but well, actually, it is convex. Our first approach, and we showed that this is equivalent. So we replaced this 0,1 loss by a convex function, and the cost function is a superposition of convex functions, so the sum of convex functions, and so it's itself convex. So question 2 is yes, it is a convex optimization problem, which is good because it has good convergence properties, right? The next question. The optimization problem for logistic regression has always a unique optimum. Yes or no? Yeah, I like it. This question is more tricky. And it's more tricky, and it's a little bit unfair because, I mean, how should you know, right?
Yeah, we have not discussed it yet.
We have not discussed it yet, and so you should actually. I mean, there should be a third option of replying, saying, I don't know. I mean, how should I know? So what we know is that this optimization problem is convex. This is for sure. But we don't know yet whether there is an optimal solution. And indeed, you will find out that in the tutorials that if the data points have actually the nicest probability that you can imagine, namely that they are somehow linearly separable, then you will have an effect like you have with this 1/x function. You remember, where we say, well, perfectly convex, even strictly convex, no problem, but there is no optimum for that. And there are certain cases in actually the good cases where you run into the same problem in logistic regression. But this is answer will be given in the tutorials, right? And this is important because understanding that and knowing that leads us to modification of the cost function in practice. Because in practice you would have a penalty that that additionally penalizes the norm of the weights here. And yeah, that's the good thing. So I mean, from this theoretical observation that it actually has not an optimal solution if the data is linearly separable, we modify the cost function in order to get a good solution for that. Okay, so this question was unfair on the one hand, but on the other hand, it should motivate you to go into tutorials and see what's happening there. Okay, so that actually that was all that I would have to say about logistic regression, and I would then go to the next section, which is about unsupervised learning. And so unsupervised learning is more, you know, I mean, it's more challenging. You don't have an output variable y that you can use for training. You have kind of model that, and I would like to start here, and also want to start with a very easy approach for that. Let's see. There you go. Yes. Unsupervised learning, and we, you know, in order to transport the idea of unsupervised learning, I start with a very, very easy example, namely k-means clustering. And perhaps you have already heard about this k-means clustering approach, but I want to put that in a kind of broader perspective of unsupervised learning. So you remember we discussed this curse of dimensionality, when we say, so we have high dimensional input, and this is sample, and it's sample in a very high dimensional space, and in that space we have very unexpected phenomena that occur. Right? Remember, for example, it's difficult to estimate the underlying probability distribution. We have the problem that samples tend to lie in the tail of the underlying distribution. Samples tend to be equidistant, and all that was somehow not very good in extracting information of it. So one idea is to use dimensionality reduction to circumvent these issues. And of course, dimensionality reduction has to be well defined and has to be like somehow graspable from a mathematical perspective. What do we mean by dimensionality reduction? Okay, and so if you want to be more precise, it's about finding a mapping from the input space to some other space, Rk, which just stick in the real in this lecture, such that the mapped samples of the input variables, right? So this is the mapped candidate here, concentrate in a much smaller volume than the original samples xi, while keeping the global structure as good as possible. That is one of my attempts to somehow make it graspable. So you know, I mean, you have, for example, data samples here, and what you want to do is you want to map them f onto some lower dimensional space with some lower volume, and for example, you map it on this curve, for example. That could be one way of how you could imagine that. Okay, so you have this data in the high dimensional space, and then you have a lower dimensional curve that does it. Okay, but also clustering is one approach that goes into that direction. Right, so for example, clustering, you say, okay, so I have high dimensional data here, and there. And what I want to do is I want to map it onto all the data that I have. I want to map it only onto 3 other points. And the other points are somehow the cluster. So, you know, I mean, you keep somehow the you keep some geometric information of the global structure, and you reduce the dimension. Yeah. You can also, I mean, one other thing is that also fits here is if you have your data like that you find like two subspaces here, and you say, well, I want to reduce the data and map it onto two subspaces, for example. Okay. So you have somehow reduced this high dimensional data into something that has a lower volume. Okay. So that I understand that this is very abstract, but this is the way I would define unsupervised learning on a very high level, what that is.
So, Martin, we are getting some questions.
Yes, I'm pretty sure about that. Yes.
Yeah.
So actual dimension reduction, isn't this just interpolation in the same dimension? So, okay, I mean, one problem that you always have in this dimensionality reduction thing is if I want to draw something, I only have 2 dimensions for drawing, and 1 dimension. You know, I mean, I only have 2 dimensions if I want to draw that on a line. So it somehow will bias your imagination. So the thing here, so this question, the difference so it will not segment the high dimensional space into four half spaces, or into half spaces, because it's very, very low dimensional perhaps. Interpolation in the same dimension. Interpolation is something else. Segmentation and clustering. What's the difference between segmentation and clustering? I haven't explained what segmentation is, so I cannot define what the difference between segmentation and clustering is. I know that in sometimes the word segmentation is used, but it's in the business context, and to me this is the same. So there is no difference between segmentation and clustering. It's just another word.
Yeah, this question is rather abstract because we also use image segmentation. So,
well, image segmentation is also, if you want, the kind of clustering approach, because you divide your you define regions in the image, and you assign it to one region. So you map every pixel, if you want, to one cluster. So it's somehow equivalent in that sense. Well, you divide your image into k regions, and you assign each pixel to one of the regions. So it's a kind of k clustering. That's how I would see that. Okay. So perhaps that also might become clearer if you have learned a few, or if you got to know a few more of the dimensionality reduction techniques. Then it might become clearer what the idea behind is. And let's start with the first one. And no, the lines would not divide it in 4 spaces, as I said, because the lines are very low dimensional compared to the high dimensional space. Good. Yes, so that's the clustering example. So the clustering example says, okay, clustering right? Take an input xi and assign it to some cluster ci, right? And the number and ci is in some class c1 to ck. Okay, so you have only finitely many values here that this clustering function call it F, can take. So more precisely, so that's unsupervised learning for me, right? I'm given some input, random variable X, or some samples of X respectively, because typically we do not have the distribution. Then unsupervised learning is the art of finding a volume reducing map F from the input space to some output space that is optimal for some suitable loss, L, that measures the deviation of the global distribution and the map distribution. Right? So we have, for example, here clusters, and here the distribution is, and we want to find optimal, clusters, optimal in some sense. The map variable set of F is called the reduced variable, and it's also sometimes called features. Just to bring that in connection to what you perhaps know about that. Right? If you, for example, I mean, if you think about the example that we had at the very first lecture, where you recognized the image of someone, namely of myself, we said, so what happened there? And what was happening is that you took this high dimensional information that you get in this image and you map it down to some reduced variable. And you can use all images that you have. You can compare them, and you map them to some lower dimensional space, and you only somehow map them to features that are sometimes abstract, but have a much lower dimension than your original input space. This is also something that happens there. Right, so example, images are mapped to features. And these features can be very abstract. Okay, so let's see. I mean, if you, how should you deal with that information? If you think that it helps you, then keep it. If you think I'm not pretty sure what it helps me, then let's have a look at it at the end of the lecture and see whether it helped you somehow. Because I understand that this is quite abstract. Good. But this is, I mean, all unsupervised learning methods that you see have these things in common. All unsupervised methods are dealing with reducing the dimensionality of the input space in some case. Would you contradict me, Umer or Ryan?
No, I think that's fine.
Good. Perfect. Okay, so in this k-means clustering example, we had, let's just formalize it. So we have given some input x in RP, or respectively training data x1 to xn, right? So this lies here somewhere in our high dimensional space RP. And our output space, so where we want to map this data, also lies in this RP, but the output is limited to k numbers, or k vectors, C1, C2, and CK. And so we reduce our volume by really restricting it to a zero-dimensional output space, right? Namely, just the finite numbers that we have here. And everything that is lying here in around this cluster will be mapped to that point here, and everything in the neighborhood of this cluster will be mapped to that cluster, and so on and so forth. For k-means, the loss function is just the squared loss. And for our empirical expected loss version, this is the thing that you want to minimize. Okay, you want to minimize the empirically expected loss 1 over n xi minus f of xi, and this f of xi is as we said, an element of the C1 to CK. Okay. So k-means clustering, if you formally aims k-mean clustering methods. There are more methods. They aim at finding a function f out of the function class that is given here. So f has not more than k different values in Rp. So this is our function class. And from that function class, we want to find the best one that minimizes this function here. Okay. Is that give you a second? So no, the CKs are not determined. The CKs are the task. So once you have the CKs, I mean, once you have your function class, you know you also have the CKs. Right, and the task of finding the task in clustering is, well, find the clusters, and not only find the clusters, but also for an input. Xi or X way of assigning it to one cluster. And this is the function that, and this is f. So f has certain output values, C1 to CK, that have to be found. And it needs to find, it needs to assign it to each point x, the new, to each new point x, the corresponding cluster. Okay.
So the next question is, how do we realize dimensionality reduction?
Well, I mean, for example, I mean, in k-means clustering, we realize this dimensionality reduction by, I mean, it's a volume reduction more than a dimensionality reduction. This is why I call it volume reduction. The distribution that we have at the beginning is distributed in the whole space, and the distribution after mapping is distributed only on k different points. So this is the you cannot do more volume reduction than this actually. So we need to find the CKs and the mapping F together. Exactly. That's correct. Yes.
How do you know the best number for K?
That's a good question. Well, that's a good question, and I can answer it very easily. If you look at the, you will get a mathematician answer to that. Okay. So the best number, if I want to minimize the empirical loss, is small n. That is our best. That is the best number, because then you assign each data point. Then you assign to each data point the new input. Each data point is its own cluster. If you do that, but of course this does not generalize, because if a new data point X is coming, you don't know how to assign it. Okay, so you have this generalization thing. And now a practical answer. In practice, you would probably try out a few few numbers of the k, because k has to be fixed and predefined beforehand in this k means clustering approach. And you would come with a few k's and see whether there is a big difference in the loss for 1k and for k plus 1. And if you say, well, if there is not a big loss between k plus 1 and k, I stick to k and don't go to k plus 1. Was that somehow clear?
Yes, I think it will become more clear when we dig deeper. So yes, the person says thank you. So there's another question.
Yeah.
I mean, people are, I think, this is also many of the students have asked, how can k-means clustering solve the curse of dimensionality when p is not reduced? Do you understand that question?
Yes, I understand that question.
I think people are kind of confusing two things: dimensionality reduction problem and clustering
and volume.
And I mean,
Yeah, dimensionality reduction and volume reduction, so to say.
Yes, so it's I don't know how to explain it otherwise. So I mean, you know, I mean, instead of having having a distribution that is somehow around one cluster, after your map, the whole data points around the cluster will be mapped into one cluster. Okay, so you will not have any volume anymore, or mathematically speaking, there will not be. You will not have nearest neighbors. I mean, you will have nearest neighbors after that, because they are all concentrated in the same point. So they are very, very near. Okay.
So I guess one example of these two cases can be that, for instance, by using dimensionality reduction, let's say by reducing the data to 3-dimensional space, we can visualize it, but we are not reducing any volume here. And by let's say finding k representatives, we don't reduce the dimensionality. Even the k representatives are in the same space, but now we have less number of points that we can only target to see that better in the data, so to say.
Yeah. Well, or let's try it otherwise. I mean, this curse of dimensionality, of course, I mean, it only occurs. It occurs if you look at the examples. It occurs if it occurs more often if each components of the high-dimensional random variable are independently distributed. And then that occurs. And with this map, you somehow have a very, very high dependency of your of the variables in the cluster, because they're always the same. Right. So exactly, we are mapping multiple dots to one dots with the same dimension. That's true. But then there is no deviation, right? If we take this if we take a toy example and say we cluster to 1 point, right? Then all data is mapped to 1 point only, and then there is no curse of dimensionality anymore, because all data samples, all the end mapped samples lie in 1 point. The question is that useful or not? I mean, this is probably not useful, clustering to 1 point, but it might be useful to cluster it to 2 points. Because then you can look at your data and then you can try to find some information out of it that you could not see beforehand. Okay. So let's just, I mean, in order that you have something to play around with data, and you might also see that perhaps it makes sense to answer these kind of questions if you do a clustering on some documents, for example. And you see, can you somehow find out any information in clusters if you have a set of documents and you know that the document is a mixed data set X of spam mails and greetings from, I don't know, your family or whatsoever, and if you don't know anything about it, does a clustering approach perhaps allow to identify these two different clusters?
And I think we discussed this in very detail with practical examples in the tutorial, the measure reduction and also the clustering.
Mm-hmm. Yeah. Well, so yes. So let's just have a look at this Lloyd's algorithm, because it's really simple, and things that look very complicated sometimes melt down to be a very simple approach. So what Lloyd's algorithm is actually doing is it inputs. Input is our training data x1 to xn in RP. We initialize with some clusters, C1 to CK. So that could, in theory, be anything. That could be anything. But typically, you try to make a good guess out of the data that you already have. And then what you do is you iterate 2 steps. And they are, from an idea, rather intuitive. So we assign each data point to its nearest cluster candidate. Okay, so we have here cluster. We measure somehow the distance. The distance is here measured with the L2 norm, here, xi minus xj, and we assign it to the cluster point, right, that is nearest for all 1 to k. Right? Once you've done that, you update each cluster candidate by averaging over all points that are assigned to it. So, and that looks like this. So you have all points that lie in one cluster, and you take the average of all these points, and you assign it to the new cluster J. And that's it actually. And then you iterate step 1 and step 2 until the cluster candidates remain constant. Okay. And well, yes, and you see that this algorithm has it's very easy, but of course you're not guaranteed to converge to some global optimum. You get stuck in local optima very quickly if you do not iterate very well. So what you do is also you run some different clusters and you initialize differently with different clusters, and then you look at the global cost function at the end and see whether you have better clusters than others. Right? This is this Lloyd algorithm. Try to play a little bit around and see what you can do here.
Okay, so I think we have some more questions.
Well, initialization of CK is random? No, probably not. Right? You would probably not use it completely random. You can use it random theoretically, but in practice, you would probably choose randomly out of this x1 to xn, I would say, out of your training data, and yeah, then run a few iterations.
And I think another question is that how can we avoid losing information when we reduce the dimension?
Well, you cannot avoid it. Well, you cannot avoid it. You're losing dimension, but you want to. I mean, the idea of the unsupervised learning is that you get rid of the information that is just noise, if you want to call it like that. But you don't know what is noise and what is not noise a priori. So you say that in unsupervised learning, the information is more in the global view of the distribution, and you want to find a similar distribution that is in a lower volume and so has has a little bit less noise. Yes. I doubt the result won't be too far from the initialization of CK.
Well, I mean, this is not necessary, right? It depends on how good your algorithm is.
Yes. Exactly. Okay. So and there are lots of other clustering approaches that aim at different that have a different distance measure here that are not measuring in the Euclidean norm but in other norms. There are convexification of that approach that lead to global results and lots of algorithms in the literature that aim at finding this function f here with different approaches. Okay, I don't want to go so much into the detail. The idea was just to give you to transport this idea of that the volume is reduced in unsupervised learning, and we will very quickly learn another method that reduces our dimensionality, and we will also see that autoencoders and deep nets are actually reducing the dimensionality and thus gather information for that. Why we need the dimension of C? The same with X. I don't know whether I got this question.
So the question is why X and the centers of the clusters need to have same dimension?
Well, you want to compare them. You want to compute the distance from one to another, and so
Yeah.
you have them here in the same dimension. Okay. Good. So that was this unsupervised learning. We are good in time. I actually thought that we are not so good in time, but we can stop perhaps a little bit earlier today, because I don't want to start the PCA today. I decided that for next time. So what we have is this unsupervised learning approach, where we say we have some input, and this is what I want that it remains somehow in your head, and that you, whenever you look at unsupervised learning method, that you keep in mind. So actually, what is behind is that the reduction of the volume of your input variables. So it's the art, and it's an art of finding that the reducing map from the input space to some output space that is optimal for some suitable loss, and that measures the deviation of the global distribution and the map distribution. Right. That was it, and yeah. Or shall we? I can ask you. Shall we start with PCA or shall we stop here? Stop.
So those of you who want to start with PCA, maybe say yes. Those of you who want to stop, maybe say no in the votes. Yeah.
I can. It's kind of 50-50, but I mean, I can already trigger it a little bit and say what it has to do with this volume reducing part, perhaps.
Yeah.
Right? That somehow gives a teaser for the next time, and that is actually here. So PCA and spoiler alarm. So watch out. PCA is actually the following problem. We have data in a high dimensional space, and I map it here. This here is in RP, and PCA aims to find here a linear subspace some RK where the data is projected onto that subspace. Okay, so we achieve this volume reducing map here for PCA in a very trivial way. We just restrict we just restrict the search space to some the search space of the dimensionality reduction to a low dimensional subspace, right? I mean, so we just say that from this map F, RP to RK, we just fix K much smaller than P. And if you do that, then of course you have a dimensionality reduction because you come from a high dimensional space into a lower dimensional space. So this is what probably has more your intuition of dimensionality reduction than this cluster thing. Although the cluster thing is also a very, very high dimensionality reduction technique because the output is 0. Right? So this is what it does. It finds a linear space, and the best is measured by PCA in a nutshell, and we will approach that next time more formally. Okay. Yes, and we will learn a little bit about singular value decompositions, or not learning, but repeating what singular value decomposition is, because it is needed for computing the projection and so on and so forth. Okay, good. Then I think that was it. And again, as in logistic regression 2, there are several ways of approaching PCA. We will come to the same algorithm, but we have a geometric interpretation for unsupervised learning. There will be a statistic interpretation for the PCA, and there will be a noise model interpretation PCA, and we will go through all of them because it shows us that all the 3 different views lead to the same approach, and the different views will also help us to generalize to different directions. This is why it's important. Okay, good. Then, and hope next week. Then with